Okay, let's get started. So last class we talked about format string vulnerability. There is one more example I want to show you guys. So we were looking at format string challenge 5. So this is the source code. To solve this challenge, what you can do is you change the value of auth. So auth is a global variable here, so you can get the global variable's address, then use the format string vulnerability to change its value to non-zero. As long as it's non-zero, it's going to print out the flag for you. But we want to make this approach a little bit more generic. Let's say instead of overwriting the global variable auth, what other approaches we can do to get this flag here? Here, basically, I want you to just change the return address on val_foo's stack frame and change it to print flag. So that's a basic idea. But to pull that off, actually, you need to do a lot of calculation. So today, let's do the calculation together. So to make sure we know how to do this one. Okay, so the idea here is there is a return address on the function val_foo's stack frame. You can overwrite that to anything you want. So with that %n, you will be able to overwrite. But there are two challenges. The first one is the number, the value you are going to overwrite is the number of characters your printf prints out so far. So the return address is 4 bytes. In 64 bits, it will be 8 bytes. So it's a huge number. It means if you want to overwrite that value to the return address, you have to print out a lot of characters first. But right now, you are printing out to the terminal. It's very slow. So this approach may not work. It may take days for you to print out those characters, right? So instead of overwriting 4 bytes directly, what we can do is we do not overwrite 4 bytes. Same as we guess the stack cookies. We do not guess 4 bytes at the same time. We guess one by one. So here, we overwrite one byte at a time. So far, we haven't talked about the mechanism to do that. So far, we're using %n to do that, right? So %n will overwrite 4 bytes or 8 bytes. You cannot do that one by one. So actually, there is one specifier, which is HH to H. So if you use %HHN, you can just overwrite 1 byte instead of 4 bytes. If you use 1H, then you can overwrite 2 bytes instead of 4 bytes. We're talking about a 32-bit machine. So this challenge, we can solve that. Another one is, what if we already print out many bytes? We already print out many characters. So the value we can write is a big number, relatively big, like 40 something. But the value we really want to overwrite is like a very small number, like 8, 6. So how do we do that? So that one is also easy to solve. We just overflow that byte. So if it's 1 byte, then 0 is the same as 256. Does that make sense? So 1 is the same as 257. So they are all 1, right? Okay. So go back to this challenge. What we are going to do is, this is what the stack looks like. We just want to overwrite the return address and change it to the address of print flag. However, remember that, so originally, there is already a return address here. So this one, the val_foo is called by the main function. So originally, there is already an address here, which is in the middle of the main function. And that 4 bytes, actually the higher 2 bytes of that will be the same as the printf print flag. So technically, we only need to overwrite the least significant 2 bytes of this address. We don't have to overwrite 4 bytes. So this is the same as what you did in the address space layout randomization one, right? So the higher 2 bytes do not really change. So this is what our exploit looks like on our server. So, but then let's try to figure this out here to how to solve this. First of all, our format string is at this place, which is 524 bytes away from the saved EBP. So that's why you can see, no, not there. Oh, so this value doesn't matter, right? We need to figure out, because in this one, the buffer is 512 bytes, but we're not going to overflow that. The vulnerability is in the printf, which we have an arbitrary write permission there. So let's check out this program. This is format string 5, 32-bit. So most of you already solved this, but we're using a different approach now. So let's say, so our input here should be some format string. Then we want to figure out the, so the program actually will print us where the return address is. So that's where we want to overwrite. That's the target we want to overwrite. So what we do is we put that address at the beginning of our buffer, which will be 8C D6 FF. So we put that at the beginning of our buffer. So after that, we want to put some, let's say, percentage here. Then now we can say let's use the 0 padding, will be clear. Maybe this is a little bit too small. Okay, so now we are trying to figure out how many percentage X we can have. We need, so we can reach to the beginning of our buffer. So if we do this percentage AX, I don't remember how many we need, so we just try here. That's 5 already, so we still do not say that. We keep trying. Nope, maybe we need one more. Yeah, so when we have, this is 7 of that, so we get our address. That's what we write there. So to prove you that, we can change this to D. You can say this value will also change to D. Okay, so that is what we have. So here we are going to overwrite 2 bytes of this. So technically we are going to overwrite 2 address. So the first one is 8C. So after 8C we are going to overwrite 8D, right? So those are the lower 2 bytes. Then the higher 3 bytes would be the same. Okay, so I add a padding in the between them. So now we still have this. So this one matches this one. So now we know this one we're going to change to HHN. Then after that, just a percentage D for padding. Then we have HHN again. So this should map to our address, but it will generate a fault here. So then what is the value we should give here? First, we need to figure out where is the function print secret, right? So we can do an m format string grep print. So you can see print flag, the function is at this location. Let's record that location. That's the location. So the lower address is 36. The higher address is 92. So 36, remember this is a hex value. So 36 is actually 54, right? I think it's 54. X to decimal. 36. We have 54. So 36. 54. This one 54. Then 92 is what? It's 146. So those are the two values we want to write to those 2 bytes. The lower one is 54. The higher one is 146. So we can, this export we're doing here, we are writing the lower one first, then the higher one second. So how many bytes we print out so far? So here we have 4 bytes, another 4, another 4. That's 12 already. After that, we have 2 of those. That's 14. So that's 4. So from here to here, that's 14 bytes. Let's write that down here. So this is 14 bytes. Then after that, we have each of this is actually 9 bytes because 8 bytes of the value and 8 characters of value and a dot. So that's 9. So 1, 2, 3, 4, 5, 6. That's 54. Okay, so that's actually big. That's already 54. So all of this is already 54 bytes or characters. But the first value we want to write here is 54. So it's already over that. So here we already write like 68. It's already over that, right? So what we can do is we can do, let's say, the value we want to get is 54. We already write 54 plus 14. Then we can we add a little bit padding here? So oh no. So we need to add a little bit padding there. So if we add padding, then we need to add a lot of value there. Let's see, how do I do this? Did I do that right? That's right. Okay. So any idea here? How do we do this? The value we want to write is 54. So 54 is the same as 256 plus 54. Then we minus what we already write, which is 54 and 14, right? So after we get that, so which means we still need around 242 bytes. Does that make sense? To get that value. So what we can do is we can change this one. So before this, the first right? We still need 200 and we need, yeah, so we can add here actually. So 242. So this one is to 442, but we missed the 6, should be 50, right? So how many is this? Let's say. This is 14. This is 14 here. After 14, we have 1, 2, 3, 4, 5. So we have 14 times 5 times line plus 250. Here I give 250 here. So that would be, what's this? $309. That's not correct. We should not have 309. We should have. We should have 310, right? There's a, I missed a dot. Oh, there is already a dot. Oh yeah, here is a dot. Okay, so that looks correct, right? So the first one, we actually, when we reach here, we print out 310 characters. So that 310 character, obviously 1 byte cannot represent 310. 1 byte can only represent 256. So 310 overflow that 256. So the result will be 54. So far, so this one we will write 54 to the lower byte, the address, the least significant byte. So after that, remember we have the value 54. Now we are going to write the second one, which is 146. So we just need this one minus this one, which should be 92, right? So we just need another, so 146 minus 54, sorry. That should be 92. So after this, we do a 92D. And this should work, let's see. What's going on? Yeah. Oh, we actually calculated it right. Okay. So when we do 250 and 92, then we overwrite that return address, the last 2 bytes, and it goes to the function print secret. So it prints a secret for us. Okay, let's change this a little bit. Let's say the first byte we want to overwrite is not the least significant byte. Instead, we overwrite the 8D, then we overwrite 8C. Okay, let's do the calculation again. So the first one we want to write is 146, which is 92. 146, same calculation here. How many bytes so far? Forgot again. Did we do a calculation? We have a calculation. Let's do it again. Okay. 14 plus 1, 2, 3, 4, 5. Right? Okay. So 14 plus 5. Then there's another. Yeah, there is actually another dot. So anyway, so this one will be 14. That's 60 here. No, 59 here. So at this point, we only have 59. So this one we need 146 minus 59. We need to override that. Will be 87, right? So we need 87 more characters. So 87 characters, which means this value we should change to 86. Because after that we have a dot. Right? That makes it 87. So here total we have 146. So after that, we are writing a smaller number, which is 52. So obviously, now we have to do 54. 54 plus 256. So that's 310. We need a 310. And before that, we already have 146, which means we need to write another 154 bytes. So after we do this, we can change this one to 154. Okay, so this one should also work if my calculation is correct. Let's see. No, the calculation is not correct. Which part is wrong? What? I cannot hear you.
Would it be 154 plus the 92 that was already there? Are we taking that into account?
92? We don't have 92. The 92 is hex.
Oh.
Yeah. Let's check this again. So this is 14. Okay, this part is correct. This part is 45. 14, 45, 59, that's correct. After 59, we need 146 times this. Is this correct? That's correct to me. That's correct. So 87. Then after that, 140. Okay, anyone see the problem? This one should not be 145, should be 165, right? Not 154, should not be 154, should be 310 minus 146, that should be 164, not 154. Yeah, so that's a problem. So we change this one to 164. Okay, we got it, right? So the hard part of this one is you need to do the calculation carefully because the value you are going to overwrite is how many bytes, how many characters the printf has printed out so far. And also, another thing is if you change anything at the beginning, you have to match it at the end. For example, here you want to add a percentage n to print out some value, but you need to add some garbage at the beginning to correspond to that one. Otherwise, the percentage n will correspond to your address without this, right? And then your address, then some garbage after the address, technically this part, will correspond to your percentage HHN. That's not a valid address for it to write, so you get a segment for it. Obviously, those A star matter, you can have anything. Okay, so any questions? Cannot hear you, sorry.
In the text files, could you just re-explain the lines you're doing where you were doing the addition and subtraction, just like where you get the numbers from?
Which number?
In the text file, where you were going line.
Oh, the text file?
Yeah.
So those numbers?
Yeah, like line 11
Line.
or like line 13. Just where are you getting?
For example, this one, you know, that is the address of print secret. So the higher 2 bytes, the most significant 2, we're not going to overwrite, right? So we don't care. We are going to overwrite the lower 2 bytes, so which is 92 and 36. So those are hex values. So 36 is 54 in decimal, 92 is 146 in decimal. Then I'm trying to calculate how many bytes we have written so far. So this part I calculate, that's 14 bytes because there are 2 underscores here. So the whole thing is 14 bytes. So this thing, so each percentage x here, because we said the length is 8. So each of this would be 8 characters. Since we have a lot of dot here, that makes it 9 characters. So we have 5 of those. Well, here we have 6 of those. So that's 54. That's 54 bytes. Then we just add them together to calculate how many more bytes do we need. Does that make sense?
So what is the 256?
256 is the value of 1 byte. The 1 byte is 0 to 155, right? So if the value we want to overwrite is a very small number, like 8, but we already print out 30 characters, we cannot reduce that number. We can only make that number higher to overflow that byte. So so what we do is we write 256 plus 8 bytes, or plus 8 characters. Does that make sense? To overflow that one, yeah. So that's how it works. Other questions?
The A's that you have on line 7, 4 A's.
The 4 A's.
Yeah. Are those, what are those there for?
So those are here because at the end here we have a percentage D here. The reason we want to have percentage D is because we're going to overwrite 2 bytes. The first one a value, the second one a different value. So in between we have to print out some characters. Otherwise they will be the same value, right? So in between them we have to print out something. When we print out something we use percentage D. So we can control how many characters we print out. But since we have a percentage D, what printf does is we look for what value to print out at the beginning. So if we have this percentage D, we do not have this 4 A's, it will look for 4 bytes. If we do not have those 4 bytes, that percentage D will corresponds to this value, which is our address for the next byte. Then the HHN will correspond to this part. Then we're not going to write to the location we want to write. That's why we have the 4 A's here. So 4 A's, the value of 4 A's doesn't mean anything. It can be anything, right? It can be zeros, whatever. Yeah. Let's say we change this to 4 6. Doesn't matter. Okay, are we good? Okay, then we move forward to new topic today. So today we are going to talk about a very, very interesting topic, which is called return-oriented programming. So return-oriented programming is, I feel it's one of the most important discoveries in system or software security in last 15 years. This is an attack that you can find in the wild right now. They are very powerful. We can also defeat them. So let's try to understand why this attack is so important. So far, we have talked about code injection attack. At the very beginning of buffer flow, we do code injection attack, which means you develop a piece of shellcode, you inject that shellcode into the program's address space, then try to execute that shellcode. So there are many places you can inject that. You can inject that in environment variable, command line arguments, or the buffer. So all 3 places, those 3 places, they are all actually on the stack. So to defeat that, we use an approach called DEP to make the stack non-executable, right? So even if the attacker can inject the code to the address space, the system doesn't allow the attacker to execute that code. So still, the attacker cannot do that. That's why another approach is to reuse the code that is already in the address space instead of injecting new code there. So we look at one attack is return to libc attack, that you overwrite a return address to a code, to a piece of code that is already in the program. So the example we saw just now, that is also a code reuse attack. We change the return address to point to the print secret. That is already a code in the address space. You didn't inject that, right? So however, return to libc attack, there are a lot of limitations itself. You can only return to functions that are already in the address space. Obviously, as a developer, you're not going to develop functions for the attackers. So attackers do not have the functions they need there. So they need a more generic form of this attack that they can do anything, a Turing-complete computing attack. That leads to our return-oriented programming attack. So return-oriented programming is a more generic form of return to libc. So in return to libc, we return to a C library function or any other function. In return-oriented programming, we do not return to a specific function anymore. We only return to some piece of code in the code section. It's not a full function. It's just the several instructions we will say later. And those instructions may not intentionally emitted there by compilers. There could be some other instructions. We re-implement those instructions in the middle, then they become different instructions. We will show that later. So return-oriented programming was proposed in 2008, something like that. Then people realize we can make this even more generic. Any indirect control transfer. So return is basically an indirect control transfer. When I say indirect means the target is determined at runtime. The target is on the stack, right? So at runtime it can be changed. So there are other indirect control flow transfers, like an indirect call, an indirect jump, like a jump instruction to a register, a call instruction to a register. Those can also be exploited. Then we have jump-oriented programming or call-oriented programming. Also, even the Linux signal handling mechanism, the sig return can be exploited this way. So there is also sig-oriented programming. Okay. A little bit about the history of ROP. So now people believe this technique was first introduced in 2005 to work around the 64-bit return to libc. We are going to see an example like that. But back in 2005, the guy who invented this didn't publish any paper, and the approach he invented was still not that robust. So back then, in 2 years after that, 2007, there was a professor at UCSD, University of California, San Diego, Hawav. I don't know how to pronounce his name. So this guy published a paper in CCS 2007. So CCS is one of the 4 top conferences. Actually, this year CCS will be next week. Not next week, this week. Actually, I'm leaving for CCS tomorrow. Will be California this year. So 2007, he published this paper called The Geometry of Innocent Flesh on the Bone, Returning to libc without function calls on x86. So in this paper, which you are going to read this week, he coined the term return-oriented programming and proved this empirically you can build any exploit out of this approach. So this is a paper. So this professor, he made a lot of important contributions to software security, system security, and also crypto. He graduated from Stanford, I believe. So his advisor is the one who invented identity-based encryption, IDC, and a lot of other things. So he already moved. He's not with UCSD anymore, I believe. He's with UT Austin right now. So in his own words, he said that in the paper, in any sufficiently large body of x86 executable code, there will exist sufficiently many useful code sequences that an attacker who controls the stack. So here's the key. You still need to control the stack. We will see later how you control the stack. You don't need to inject code to the stack, but still control the stack. The attackers will use this to cause the exploited program to undertake arbitrary computation. So basically, you can use this to do anything you want of the attacker. So 10 years after this paper was published, it got the Test of Time paper award. We mentioned this before. Test of Time, all four the big four conferences that have Test of Time paper award. Very hard to get. And also you notice that this is a single author paper. So when this professor published this paper, he decided to do this by himself. He didn't involve anyone else. He realized this is a very important discovery, so he did everything by himself. Didn't involve his PhD students there. Very interesting, yeah. There is a longer version of this paper with more details, published 4 or 5 years later in the best security journal, which is called TSEC. Right now they changed the name to TOPS, ACM, Privacy and Security. That's the best security journal. But most security guys, we do not really publish in journals that often. We're publishing in big four security conferences. So this paper is very long, like 40, 50 pages. The CCS paper is like 13 pages maybe. So this one has more details, but it's too long. I do not ask you to read this one. Okay, so afterward, what is ROP, or what is return-oriented programming? So recall that when we do return to libc or return to any function in the address space, if the function we are returning to do not have any arguments, we can actually chain them together. We can call arbitrary number of functions, return to arbitrary number of functions, right? So this is from our very first maybe the third class. I showed you this. But if they are parameters, we cannot chain them together. So first of all, this is a 32-bit one. So in ROP, we are not going to return to full functions. We return to small piece of code sequences. We call them gadgets. Okay? So they are just several instructions. And all those instructions, they end with a return instruction. So that is why it's called a return-oriented programming. So in jump-oriented programming, they always end with a jump instruction. In call-oriented programming, they always ended with a call instruction. But those instructions, they are all do indirect control flow transfer. Okay. So in this class, we only talk about return-oriented programming. We do not talk about others, but the ideas will be similar. So jump-oriented programming is a little bit difficult to pull off, but if you get this idea, you can understand those as well. So we want to chain those code gadgets. Each gadget ends with a return instruction. We want to chain them together. Even though a gadget only have 2 instructions, 3 instructions, very small. If we chain enough gadgets together, we still can do something useful. Like we can print out the flag in a file. We can get a shell from the system. All right. So what is the return instruction after all? So far, we are looking at the instruction level. But the instructions are just bytes encoded by Intel, because it's Intel's CPU. So in the x86 CPU, the return instruction can be just those 4 opcodes. It can be C3, CB, C2, CA. Okay? If it's C2, CA, there will be some parameters, 2 bytes parameters. So you can see that. So if there is a C3, the byte value is C3. That can be viewed as a return instruction. But a C3 can be anywhere. It can be part of your address. So if you go there, it will still can be viewed as a return instruction. So the x86 instruction set is very dense. Even if you generate some garbage, they can be interpreted as valid instructions. So that is how you design an instruction set. You want to make it dense. So the code generated, the binary code will be smaller, right? If it's not dense, then the binary will be larger. But it's so dense that, and also the instructions, they can be variable lengths. We have seen instructions that is only 1 byte, like the return, C2, C3, is only 1 byte. Then we also say, let's say there is a core instruction with 4 bytes of address, that's 5 bytes. There are instructions like 10 bytes, actually. Maybe take two addresses. I'm only talking about 32-bit. If 64-bit, it would be even longer, right? So the instruction set is so dense that even garbage can be something valid. Let me just prove that to you. Let's try to generate some garbage. So how do we generate garbage on Linux? We just do a cat, random, not device, random. So when we do this, Linux will generate a random number for us, right? A lot of random. So we just take, let's say, we just take many, how many? That's too many. So when I do XXD, I get the hex value. Then I just do a head, maybe 40. That should be enough. Not D. H. A. What? M? N? Okay. So now we get a lot of, we just copy those. Oops. I don't know how to copy this actually. I will do X here. So this is the random data we just generated. Okay, you saw I just generated random data. So this is a website some of you have been using. Then we just put some random data here. Then we disassemble this. Then you can see the random data can be interpreted as valid instructions. Of course, if you really execute those instructions, you probably will get a segment fault, right? But they are still valid instructions. And if you just move some of them, so this one, we delete the first one, doesn't work. But if we keep deleting another one, now we can disassemble again. Right? So the instruction set is very dense. Even random data can be valid instructions. So the tool we're going to use is something to find the rob gadgets. I'm not asking you to write programs to find the rob gadgets. So the tool we're going to use is just a rob gadget Python. So we already installed that in our server for you. So later you will see how to use them. There are also other tools you can use. On our server right now, we only install this one. Also, you can use the Pong tools to do a lot of hacking. In my class, I do not really ask you guys to use that because I want you guys to do things byte by byte instead of using advanced tools. Yeah. Okay, so how does those tools find the rob gadgets? Remember, what is rob gadgets? Rob gadgets is just a sequence of instructions which end with a return instruction. That's it. Let's say we have some byte sequence here. We have 8 bytes. if we disassemble this 8 bytes from the very beginning, we get 3 instructions. We get increase EAX, XOR EAX, then move some value to EAX. So that's 3 instructions. But if we disassemble those 8 bytes from here, basically we do not care about the first 4 bytes. We disassemble from the 5th bytes. Then we get 2 instructions. The first is a store. The second is a return. Because basically we are disassembling from the middle of the 3rd move instruction. And there is a stage 3, and that stage 3 is a return. And before that, so the stage 3, you can say the stage 3, if you interpret this way, stage 3 is just a part of the address. That's just part of the address. But if we let's say we just disassemble from stage 3, then stage 3 is a return instruction for us, right? So those tools, what they do is they just disassemble instructions byte after byte. For each byte, they try to disassemble and say if they can get a sequence of instructions end with a return instruction. After that, they move to the next byte, disassemble that. So that's how they can get those, find all the ROB gadgets. So each gadget end with a return instruction. Okay, so now we go back to our very old, this is a challenge we did. This is like the first or second challenge we did in this class, right? So this is the overflow return 3. The main function print out the print secret. There is a print secret function. The print secret function takes 2 arguments, fixed values. Compare those fixed values. If your inputted argument equals to that fixed hard-coded value, then we'll print flag for you. Otherwise, print IPT the full. So we did the 32-bit version of this and also 64-bit version of this. So 32-bit version, what we did is we overwrite the return address on vol-foo's. So vol-foo has the vulnerability. We overwrite the return address on vol-foo's stack frame. We put those 2 arguments on the stack, right? That's in the 32-bit, that's what we did. We have the return address, then we have the parameter 1, parameter 2. For the 64-bit version, however, this approach doesn't work because the parameters, they are not on the stack. They are in registers. The vulnerability we have here, this one. This is a vulnerability, the gets. This is a memory corruption vulnerability. You can only corrupt the memory. You cannot corrupt the register. So here, no matter how many bytes you overwrite, you are only going to overwrite the stack. You are not going to change any register value, right? So for those who solved the 64-bit version for this one, what you did is instead of jumping to the beginning of print secret, you directly jump to maybe print flag, or jump to the middle of print secret, which calls print flag. That's how you did it for the 64-bit version. So now we are going to use ROP to jump to the beginning of print secret, which means we have to have those 2 registers, those 2 parameters have the correct value. So how do we do that? First, let me remind you that the 2 registers, they will be in RDI and RSI in the 64-bit. And this is what our exploit looks like. So I'm directly giving you the exploit here. Then let's see if we can understand this exploit. Okay, let's see if we can understand this. So this is our stack. have the buffer. This is 64-bit, so the saved RBP, so it's not saved EBP, saved RBP, which is 8 bytes. The buffer here is actually 6 bytes. So you can say here is RBP minus 6. That's the input to gets. So this whole part is 14 bytes. Then this part is supposed to be the old return address, right? So our exploit will look like this. It only has how many bytes there? Each of them is 8 bytes, so we have 5. So we have 40 bytes. The whole exploit is 40 bytes. In the first return address, what we put is, we put a gadget's address there. The gadgets we're looking for is a pulp RDI return gadget. So that gadget only has 2 instructions. The first one is pulp EDI. The second one is return. Somewhere in the memory, we will find those 2 instructions. We just need to find those 2 instructions and put the address here. Then after that, we are going to put the value 1, 2, 3, 4, 5. That's 8 bytes, so it's long. Then after that, we have another address of pulp RSI return. Then deadbeef, then the address of return secret. So after the very last one, we are going to return to the function print secret. And also we will have RDI with this value, RSI with that value. Okay. So let's say, then let's try to understand how it works. Okay, let's say at this point, we just put our exploit onto the stack. This is what the stack looks like. We are about to execute the instruction return in valfoo. This is valfoo's stack frame. So at this point, where RSP points to, RSP should point to the return address, right? Which we already overwrite. That's the return address we overwrite. So now we execute the return instruction. So then, because we execute the return instruction, the IP, the program counter, will be updated to what? To the address of pulp RDI EDI, right? So after this, the RIP will point to the address of pulp RDI, which means the next instruction we are going to execute will be pulp RDI. But the RSP will move up 8 bytes. So RSP points to this value, okay? Then the next instruction we are going to execute is pulp RDI. So very conveniently, we are going to pulp where RSP points to. So we are going to pulp this value into RDI, okay? So after this one, now, after we execute the pulp RDI, what is the next instruction to execute? Which one? That's a return, because after we execute pulp RDI, then we have the return instruction. Now we have another return instruction. The return instruction will pulp whatever RSP points to RIP. So we're going to have the address of our second gadget, pulp RSI return, put that address into our RIP, right? Now the next instruction we're going to execute will be pulp RSI. Then it's going to pulp the deadbeef into RSI. Then after that, there's another return instruction. That return instruction will, after we do that pulp, the RSP will move up for 8 bytes. Then after that, RDI have the deadbeef. RIP will have the address of return. Then we're going to execute return again. Now, when we execute return, the RSP points to the address of print secret. Then we go back to, now we return to print secret with the correct argument value. Okay? That is how it works. that will be our gadgets. So you can see here, we didn't inject any code here. We only inject data to the stack. The stack is not executable anyway, okay? So even if we inject the code, it's not going to work. The data we inject there, some of them are technically code pointers, the address of the gadgets. Then there will be just two values. So the next step is to find out where are those gadgets. So I have a template for you here. So when you do this challenge, I suggest you to use my template. There are a lot of challenges as well. I suggest you to use this template because if you just type all of those will be crazy. That's too many. Okay, so let me explain a little bit about this template. So this is a Python 2 script. What I do is at the beginning, we have the padding. The padding in here, I have 14 bytes because I already explained. This part is 14 bytes. The buffer is 6. The saved RBP is 8. That's 14 bytes. So after that, we just pack this value. So what does this mean? This means this is little endian. The Q means this is 8 bytes. Then I suggest you to put the instruction here so you can understand what you're doing. So here we are actually looking for those instructions. Pop RDI return, pop RSI return. Okay. Then we just print out. That will be our exploit. So let's try this. Just copy this. Go back to our server. This one would be overflow return 3. Overflow return 3, 64 bits. Yeah, 12 of you actually solved it using the other approach by directly jumping to print flag. And now we're going to do something different. So the tool, let's put let's use this one. So I will put the exploit there, but this exploit is actually the Python code. It will generate the binary exploit, so I change this to executable. Okay, so this is our exploit this way. Then we go back here. Then we look for those gadgets. The tool we're going to use is called a rob gadget. Rob gadget Python. Then it will the command is binary, I believe. Let me see what the command is. The command is binary. Then you can specify an offset there. Binary. So we can look for the gadgets in any code in the address space, which means the program itself and also the C library. We can let's find the gadgets in the program itself, because this one is simple. We only need several gadgets, so it should be okay. So you see, when we look for these gadgets, we find 78 gadgets in this program itself. All of them end with, this tool actually finds all kinds of gadgets, not only return-oriented gadgets, it also finds jump-oriented gadgets and call-oriented gadgets. You can see some of them end with a call instruction, some of the jump instruction, some of them just return. So now we just focus on the return one. So the gadgets we're looking for is a pop RDI return and a pop RSI return. So we can just do a grep here, RDI. You can see we do have a gadgets there. There is a pop RDI return. Then let's say RSI. Do we have RSI? RSI, we do not have a gadget. Oh, we do have one. This one. So this one we have a pop RSI, pop 15, then return. Okay? So which means we just need to put a lot of garbage on the stack to pop that into R15. Then we can use this gadget. Make sense? Right, that's so those are actually runtime addresses. So what we need to do is we only need to change this exploit a little bit. Let's say the RSI address is this. We just copy this one. That's the pop RDI. Okay. Then this one we're going to use a different gadget. So I just write it here to remind me myself what is the gadget. This is the address. So because of that, we have two pops, which means we need another some garbage value on the stack, right? So here we just do, we can do just a 0. Okay. So this one is for the pop R15. We don't care about the value of that, right? Now, then we also need to get the address of print secret. So we just do an M of this one. Grep print secret. This one we're going to call print secret, not print flag. Okay. Oops. So it should be this. Okay. So it looks like we have our exploit here. So this is a script. Then we just run this. It should print out our exploit for us. So it print out our exploit. That is our exploit. So let's just let's try if it works. So the exploit, we pipe it into overflow. No, buffer overflow. Yeah, it works. But probably you still do not understand why it works, right? Then let's debug this. Let's debug this step by step so you can say why it works. By the way, when we debug it, we're not print out the flag, but you can see everything before that. So we just debug this program. How do we do this? Buffer. We set a breakpoint at val_foo. We run this one using the exploit. Oh, we didn't. No, we have to. Hold on. Let me get the exploit out somewhere. So let's output it to temp exploit exp. So because this one is actually our Python script, we have to execute that to get our real exploit, which is a binary, which is here. I think that is correct. Let's take a look. Yeah, that is our exploit. Now we go to buffer. We set a breakpoint at val_foo. We run this program, use our exploits, which is exp. Okay. So now we're running our program. Right now we are at the beginning of val_foo. So nothing is overwritten yet. So on our stack, now if we examine RSP, we should have the return address. The return address should be part of the main function. So it's this one. And if we just disassemble main, you can see that 1365 is actually this one, right? Here we have call val_foo. After that, we have 1365. So that is correct return address at val_foo. Now let's disassemble val_foo. So val_foo is small. So we know the vulnerability is the gets. After gets, we're going to overwrite, we're going to put that 40 bytes on the stack. So let's set a breakpoint here. Now we have, we set a breakpoint, we continue running. Now we're still in vol Now we are at the point right after gets. So the stack is overwritten. Let's examine that. Let's examine 5Q from EBP, RBP, should be 6. Is that Q or W? Not W. What's the one I should use? What is 8 bytes? A G, right? I think it's G. Yeah. Okay. So say this is what we have on the stack. The overwrite was successful. So 8 bytes, 14 bytes in total, 6 bytes in buffer, 8 bytes in saved RBP, which is that 4141 thing, right? After that, that's our exploit. The first part is the address of our gadget, right? The second is that value. Then another one is the address of a second gadget, pop RSI. Then 2 values, because we have 2 pop. Yeah, this one we actually have, our gadget is 48 bytes, so we should have 7 of those, print of 7. Then the last one is our return address to print secret. Now let's keep debugging. Now we want to go to the return instruction to see what happens. We use ni, more. Now we're in the return instruction, okay? So now if we examine what RSP points to, that will be our target, our first gadgets. So we do SI. Now we are in our first gadgets. So see, our first gadget is in the function libc CSU init. That's where our gadget is. When we look for the gadgets, we didn't care where it is, right? But if we do a disassemble of this function, I hope it's not too big. Oh, this is a big function. Oh, it's not that big, right? So where are we? We are actually at 13 EC. We are at 13 EC. Look at this, when we disassemble this function, look at the address. There's no 13 EC here. So this function, it doesn't really have that instruction, pop RDI return. What it has is pop 15 return. But that pop 15 takes 2 bytes. If we only take the second byte, it gives us the pop RDI, right? So you can see here, we have the address E2 here. So we are jumping to the E2 is the pop 15, R15. That's 2 bytes. We jump to the middle of that. Then we got pop RDI instead of pop 15. So we can go back to our website to prove that. Let's say, we want to say, let's see, pop R15 return. The return doesn't matter anyway. So pop 15 will be 3 bytes, 2 bytes, 41, 5F. If we do pop RDI, it will only be 5F. See? That's why if we jump to the middle of that instruction, we get a new instruction. But that original function doesn't really have, the compiler didn't intentionally emit that instruction there. Where are we? Right here. Okay. So now we are in our first. Now we are going to execute a pop RDI. We do pop RDI. Then if we examine two instructions from where we're at, next we're going to do a return again. So this return, we're going to, since we're going to return, so we know we just need to do exam RSP, so we can know where we're going to, why it's a loop here. We're about to execute the return, so we shoot the RSP. So what's this? We should return to wherever RSP points to, right? Let me see, where are we? Instructions, IP. So we are at here. RSP. What's going on? Let me try one. Did I miss anything? So now we are in our second gadgets, but RSP, why RSP is this value? What did I miss here, guys? This RSP should not be this value, right? But it is running correctly. So I'm a little bit confused where we are. IP, so we are going to execute this one. So this is a pop. So this pop, then will be the second pop. Now we should be in the return again. So if we examine the stack, we should have, hold on, just a syntax error here. Oh yeah, just a syntax error here. So now we're going to execute the return instruction of the second gadgets. So the RSP should point to our third gadgets. So in this case, we don't have the third gadgets. We have the return to secret, right? So this is actually the address of return to secret. Now we do one more instruction. We enter print secret. Now we enter print secret, and print secret will use our SI and RDI as the argument. Then here we can say RDI, RSI. But RSI and RDI, we already put the correct value there. We do RDI, print RDI. Let's do X. GX. Hold on, what's the syntax? GX? Huh? Which stash is it? Should be this stash? GX? 1GX? Okay, let's just do print. How do I print this in hex? Slash X? That work? Oh, okay. Slash X. Okay. See, that's a value we have there, right? So the RSI will have the dead beef. So we successfully put the two values there. Then from here we just we are at the beginning of the print secret. We just execute print secret. But this one, because we're debugging, we don't have a privilege. So that's why we cannot open the flag file. Okay. So, any questions? So that is our exploit. we changed this a little bit. Well, we probably can find the RSI in the C library. Let's try to find that one. We didn't use exactly this gadget. We have that pop RSI, pop 15, R15. Let's try if we can find these gadgets in other places. So if we do a LLD, this program, it will tell us LDD. If we do a LDD on this program, it will tell us where everything is loaded and what is loaded. So here we are loading, say, some libraries, and this one is a C library function. Most of the program were linked with C library function. So, and it says C library function goes here. So let's say if we can find that gadgets in the C library function. So ROP gadgets, binary. So instead of finding the gadgets in our program itself, we go for the C library. And how many gadgets can we find here? We find 100,000 gadgets there. Okay, not only return gadgets, also jump gadgets. Then we are interested in the pop what? SI or DI? Because DI we find one, so we are only interested in pop RSI, right? Oh, see, there is a gadget. Okay, so for the C library, we can actually find the gadgets like that. Let's try that. But this address is only the offset in the C library. That's why we need to calculate that. We use LDD again. We get the C library goes here. Then we tell this tool. We want to add an offset there. That's our offset. Then it will add the offset, the base to this address. Then this is the address of the gadgets we're looking for. So we go back to our exploits, which is at temp E, I believe. Yeah, temp E. So now we are going to, where are we? We are going to change this one. So we do not have pop 15 anymore. So we do not need this one. This one we change to the new gadget's address. Go back here, run temp E, pipe into this one. No, there's a syntax error. What's the syntax error here? What?
You removed the dead beef.
Oh, I removed dead beef. Oh, I removed the wrong one, right? Okay, so let's go back to our. Did I remove 2 lines there? Looks like I removed 2 lines. So this one is. Oh, yeah. I see what's wrong. So this is the one I should change. This one should be the dead beef. Yeah, this one should be the dead beef. Right. This is a dead beef. That's RSI. Yeah, that's right. Then we need to this address. We put this address in that location. Okay. Syntax looks correct. Okay. So now we're using our gadgets from the C library. We also get the flag. Okay, let's take a break. When we come back, we are going to say more advanced one. Instead of jumping to print secret, we are going to have a full gadget that we can print out the flag. We do not rely on the print secret function that is already in the address space. Okay, let's take a 10 minutes break. Yes, that's a good point. That's why ASR is really useful, but there are ways to bypass it. Yes, well, sometimes it's not only you need to guess. I mean, there could be information leakage or to infer where things are.
Oh, so you get the offset on run. That's the idea. And then you load that on.
Yes, there's some kind of, there could be other bugs to leak some kind of information that you can infer where they are. Yeah.
But it is like statistically possible that you find any instruction in the binary of libc. That's the thing.
Yes.
That was the contribution on the product. Whatever happens because the instruction set is so dense.
Yes.
Then you can basically jump around to any instruction.
So when is ASR invented? I don't remember. Also 2000, early 2000, right?
Yes. There was the other link that was in 2016.
Yeah.
That was about
That one.
runtime changing.
Oh yeah. That's it's way before that. It's probably, I think it's getting to the kernel probably 2008 or something. Yeah. So probably it's 2007. Yeah, but still, now the tags are, well, in real tags you need to combine a lot of texts together to really make it work. Our class will break it down. That's what I say.
But this tool can in fact but how would you break this tool? How would you stop this from changing instruction set? Stop this from happening?
There are many, like we discussed, all other defense, right? There are direct defense, there are indirect defense. Some defense make it hard. So what really stops this is something called control flow integrity, which we will talk about. Okay. So if your system can strictly enforce control flow integrity, which means any control flow transfer is a valid one approved statically. Okay. At runtime, I proved that any control transfer is something I allowed when I do program analysis. But that is very complicated. First of all, the idea is beautiful, but it's very complicated. Yeah, we do some control flow integrity research in our lab as well on low-end devices. It's very complicated. Then there are some other approaches can make things harder, right? Like you said, change the instruction set. Let's say we do not change the instruction set, but let's say we change our compiler. The code our compiler generates or emits doesn't have any return. Doesn't have C3. Okay, even if there's address is C3, we generate more than we don't have C3. We don't have C3, CB, whatever.
Yes,
right?
similar to the shell code.
Yes, but there are other attacks. If return-oriented program doesn't work, but jump-oriented program may work, right? So those approaches, you can publish a short paper, but it's not going to really be useful in real work. Then the next one is to, at hardware level, because all of those defects you have to think about performance. That's why a lot of temperature when it's enabled in your computer, the indirect control flow has to end at NVR64. Has to be under that instruction. If you jump to other instructions, it will crash.
As any instruction get coded up the hardware,
Yes.
it has to every instruction valid has to be.
Yes, but obviously this is not perfect one, but it can defeat a lot of attacks and it's super fast. Yeah. It's like a stack cookie, right? Stack cookie is a super simple idea, right? But it's not yeah, for many years it has been used for. Yeah.
It's crazy.
It is, yeah.
Following along with you and tried doing this as well, and I'm not seeing, maybe I missed it while you were going through it, but I changed this one to be the top other side because we wanted to see that. Oh, yeah.
This one here is this is not. This is top side return. This right now is top side top 15 return.
Yeah.
Yeah, that's why after this garbage bag
Oh, okay, so should I like,
here and another after deadlift and another 8 bites, whatever.
oh, okay, that's what I missed when you were doing this.
Yes.
Okay.
Yeah.
Okay, thank you.
Otherwise, it wouldn't work. Yeah.
Thank you.
Okay, I think everyone is back. Okay, so now I hope you get a feeling why the original paper is called the geometry of innocent flash, okay? Because those bytes, those instructions are innocent. They were not even there, right? So now I hope you get that. So you can see the idea here is kind of like breaking up a Lego, right? So the original program is like who is this guy again? Yoda, right? It's like a Yoda. Then you break it down to smaller pieces, then you reassemble them into something malicious. Okay, so that's a basic idea of ROP. So there are many useful gadgets I want to mention here. They will help you when you do your homework. I do not intend to make the ROP, especially in the final. There will be a ROP challenge, but I will not make it too difficult because this one can be crazily difficult. Right? You can spend days on this. Okay, some use for gadgets. For example, if you just want to skip some data on a stack, you just have some pop, just like what we saw just now. We do a pop 15 there. We couldn't find the gadgets we're looking for. Then we just have another pop. Then we just put some garbage on the stack. It works. So that's one example. Then if we so there is lop. So basically return itself is a lop. It's going to make the RSP move up or ESP move up. That's it. It doesn't do anything else. It just go to the next item on the stack. So your control information is actually on the stack. So you need to, as an attacker, you need to control the stack. However, if you cannot control the stack, there is also a gadget to help you. There is a stack pivot gadget, which exchange the value of RSP and the value of a general register. Which means you can put your export anywhere, put that into the address of that into RAX, then do an exchange RAX and RSP. Then your export is not on the original stack anymore, right? So this is also a very powerful gadget. So by the way, this instruction exchange, anyone know why do we have this instruction? So in your OS class, operating system class, you probably designed something called like a lock, a spin lock or whatever, a lock. So to implement a spin lock, you need instruction like this. Otherwise, well, you implement that C level, but without an instruction like this, you cannot implement the x86 architecture actually. Okay, then, so the previous example, we didn't really make any system call. But if your program wants to do something useful, you need to make a system call. Like if you want to read a file, print out a file, that's at least 2 system calls, read and send file. If you want to get a shell, then you also need to do the EXE system call. However, it's very hard to find the system call instruction gadget, okay? The system call whatever, then return. It's very hard to find that. Usually they do not exist. So in this way, we do not have to use a system call instruction directly. Instead, we use this approach to call the C library function, the C wrap of those system calls. So let's say another example. So we are going to do overflow return 4. This is a challenge we keep revisiting. We have been changing its compile options many times. Now we're going to change its compile option again. Now the options are, there is no stack cookie, so you can't override the stack. However, the stack is not executable. So previously, you have been using the one with stack cookie and bypass the stack cookie, right? So this one, I only want you to focus on the ROP, so you don't need to bypass the cookie. So we disable cookie. Stack is not available. Stack is not executable. So we're not going to do. So imagine, let's say, this is our share code to 64-bit share code to. This is actually 32-bit share code. To open a file and read, we just do an open system call, then we just do a send file, 32-bit. So imagine what the stack should look like if we do a ROP on this. It should be some gadgets to set up the registers. Then we make the system call. And we need to find gadgets like this, syscall return. Okay. Unfortunately, we're not going to find a gadget like this. So this approach will not work. Instead, we're going to use this approach, very similar. But instead of finding the gadget of system call return, we are directly calling the function open, the CLibrary function. So when this function returns, it still returns here. So we keep running this, then we have the send file. Okay. So the exploit where, let me remind you this vulnerable function. Very simple one, just a val foo, there is a buffer, then you can input as long as you want, that's it. So this is what our exploit looks like. Same as last one. I show you the exploit, then let's make sense out of this madness to say if that makes sense. Okay. Two goals. The first, call the open. The second, call send file. Both with correct parameters. So first we have the padding, 56 bytes. After that, so this is the function, the first function, open. This should be flag, not a .secret. So because several years ago, I'm doing everything on my local machine. We don't have the server, so I have a local file called .secret. So now it should be flag. So the address of this string should be in the register RDI. RSI should be 0. Then after that, you call open. The return from open will be in RAX. Then that return will be the second argument of the send file. So that value should go to RSI again. The RDI should be set as 1. RDX should be 0. RCX, this one, 1000, I believe, is the size. So it doesn't have to be 1000. This one is the file descriptor of the std out. That's why it has to be 1. This one, I don't remember what this is, but it should be 0. Okay. So the first thing is we need to put the string we need to put the string /flag in the address space. Okay. We already know how to do that. We can put that into environment variable. We can have even a lot of slash at the beginning. That's one approach. Another approach is I'm going to show you here. It's a little bit different, but that approach actually will be easier. But this one also works. Let's see. So the first gadget we will have is pop RDI, which means the next item on the stack will be popped into RDI. And the next item here, I actually have the address of the .data section. So a program has many sections. .text section for the code, .data section for the global variables, right? Which means that section is writable and readable. More importantly, it's writable. We are going to write the flag there. Okay. We can put it in environment variable, but this one I put it on the data section. So I find out where the data section is, put that address here. Then that address will be popped into RDI. Then we go to the next, the return, bring us to the second gadget, which is pop RAX return. Now here we have this string here. this string that's 5 characters. That 5 characters will be put into the register RAX. That fair? Okay. Then we are going to find another gadget, which is move data from RAX to that memory location RDI. So basically, we are writing those 5, the string, to the .data section. That's what those gadgets are for. If you put the string in environment variable, you don't have to do that. Then after that, we pop RSI return. What we're trying to do is this one. We're setting RSI as 0. So that's why after that, we have a 0 here. Then after this, we are ready to call open. We have RDI, we have RSI, we are ready to call open. So we call we return to the open 64 here. Then after that, we keep moving. So the value will be in RAX, right? Then we move RAX to RSI because we need to move that to RSI. However, we do not find a gadget like move RSI RAX return. We do not find the gadget. Instead, we find this weird gadget. This one, shift this, repeat this several times. But so we don't care about the ECX value. So no matter how many times they shift, so ECX probably is 0 at this time. So after the shift, the repeat is not going to do anything actually. So this part, it doesn't do anything we need. It probably doesn't do anything actually. Okay, so after that, we set RDI as 1. That's this part, the first argument of send file. Then after that, we send RDX as 0. For the same reason, we cannot find a pop RDX return gadgets. We use this gadget. That's why we put another 1 on the stack. The value 1 doesn't mean anything. We're not using R12 anyway. Okay. Then after that, we pop RCX, which we set 80. So 80 maps the solid here. So that's a size. So I'm not really using 1 solid, just 80. Then go to send file. So after that, we are basically, after this one, we are actually done. So this one is the exit. This one is the exit system call. So here, you see, I would directly use the system call. Because instead of using a raw gadget, return gadget, because after this, we don't care what happens anymore. Okay? But those ones, we cannot use syscall because there's no syscall return. So we have to call those library functions. Okay, make sense? So when you develop a ROP export like this, basically you are translating your original share code. You first need to understand why your original share code works. Then you find equivalent gadgets can do the same thing. So you kind of like write this part. Then you find out where are those gadgets. Then you put them onto the stack. Okay, so the rest of the class, I want you guys to work on the first one and this one by yourself. I will work around to help you because same as the format string. This one is also very tricky to understand. So I hope you can stay here to work on those two. Those are your homework. There are 3 challenges in the homework this week. The first one is the format string one. Then will be the previous one and this one. You can start with the first ROP, then work. If you finish that one, then you can work on this one. Okay? It's because of that. We're not printing slash. We're printing flag. That's why you have to be in the right folder. We're printing out of the current flag. Yeah, if we add a slash there, problem solved. Yeah. We didn't do that.